My guest today is Steve Mildenhall. Steve is Assistant Professor of Risk Management and Insurance and Director of Insurance Data Analytics at the School of Risk Management in the Tobin College of Business at St. John's University. Steve has 25 years' experience in the insurance industry. Prior to joining St. John's in 2016, he was Global CEO of Analytics at Aon plc, based in Singapore, and head of AM Benfield Analytics. Steve received his PhD in mathematics from the University of Chicago. He is a cryptographer, which we'll be talking about today, which I only just learned, and maybe he did too. Steve, welcome to the show.
Thanks for having me back.
So this following our Not Unreasonable book club premiere, maybe we'll continue to call this a book club, although more of a learning club, study club. This was your idea to do this show, Steve, and I really appreciate you suggesting this as our round two, because blockchain, Bitcoin, these were concepts, technologies that I had been, to be honest with you, call it relatively speaking dismissive of, and that relative is relative to the euphoria and intense emotion that it stirs up in everybody else. I thought it was a little bit overrated, but through my research over the last couple of months, since we've been talking about this, I've come around and I do believe it's amazing stuff. So I'm looking forward to getting stuck in. One thing that I always am concerned about when talking and hearing about Bitcoin is how just immediately goes abstract. And we're going to get abstract today. We're going to talk about some things that most people aren't familiar with. But maybe we can begin with a list of, or at least a quick conversation about some technologies that Bitcoin enables, some blockchain examples. Blockchain enables, so Bitcoin is the number one example of this cryptocurrency, but what are some other examples of things that exist out there?
Yeah, so in the insurance space, there's a few examples at the moment. There's a group called Ethereum, which does travel insurance, which is all done on a blockchain database. There's another company called Everledger, which stores information to validate diamond ownership. So the idea here is you've got a database that's immutable and is certifying ownership of something. And they've got, I think, over 1 million diamonds in their database at the moment.
And I came across a quote from a guy named Chris Dixon, who is a managing partner at a venture capital fund in California, and he's a real Bitcoin blockchain guy and manages their crypto fund, as they're calling it. And he said, and here's a quote of his. So the first and most important example of blockchain use is digital currency, made famous by Bitcoin, but as we've discovered over the past few years, many other software components can be constructed using the building blocks of trust. Smart contract platforms like Ethereum enable the creation of, among other things, application-specific currencies, that being the ICOs you all hear about, digital property rights, which you touched on there a second ago, open financial instruments, software-based organizations, and that reference is actually to a coin which is working as a share in companies in the specific coin specification that he's mentioning there, which is interesting. From these components, in turn, new infrastructure and applications can be constructed. For example, developers working on upgrading the core infrastructure of the internet, including storage, networking, identity, distributed corporate computation. Stablecoins can enable more mainstream user experiences for digital payments and financial services. Crypto goods, such as there's a funny little collectibles, crypto collectibles, you hear about those? Can unlock new experiences and business models for games and other forms of media. Entrepreneurs are developing crypto-powered financial services, like the tokenization of traditional assets and payment services of the unbanked. We expect many other applications to emerge in the coming years. Some more of the list I have. There are loyalty systems, there's digital IDs, and equity markets, energy trading, medical records, tracking drugs from pharmaceuticals, supply chain management. Holy cow. There's so much here. It's overwhelming, isn't it?
Yeah, so I think in that same podcast he talked about we've got a new capability that's come along, and it's as powerful as computers were originally, it's as powerful as the internet was originally, and we're at the same point as we were with the internet in, I don't know, about sort of 1987 or something, where you'd log onto a page and it would be a few bits of HTML.
What the hell is this going to be used
and the
for?
image would load like pixel at a time, and you'd go, what are we going to do with this? But it truly is enabling this authorityless trust between individuals who don't know one another and have no reason to trust one another. It's a brand new, super powerful capability.
And so we kind of coming to, and this would be the core of our conversation today, of what is it and why does it matter? And one of the things that occurred to me over the course of my research, or became clear to me, is that actually there are precursors to Bitcoin. And so we're going to start off talking about Bitcoin and what is inside Bitcoin and how it works, and then that will evolve into a conversation about Ethereum and other technologies and then beyond from that. But what surprised me about Bitcoin was that there were a couple of cryptocurrencies that were attempted and were nearly successful. One of them was called BitGold, which uses, and we'll use this as an opportunity to talk through some of the technologies underlying Bitcoin. BitGold, which used the proof of work idea and uses, and that being something that computers can a problem they can work on in order to validate transactions. And so one of the key problems with that Bitcoin solves is when you have to track currency, you need to make sure that everybody knows where everybody else's currency is, and so that nobody steals it, right? And maybe, Steve, you can talk a bit about how that happens.
Sure. Well, I mean, I think it would be best if we sort of started at the beginning with the components, and then we'll lead up to that. So when we talk about a blockchain, and Bitcoin is an implementation of a blockchain, there's four major components to this. It starts off simply, it is a database. So we're all familiar with databases, and it's what's called a chained key value database. And you can think of that as the key value would be like a database made up of index cards. The key is the index on the index card, and the value is the content you're storing in it. And you can store anything in it, PDFs, images, text, whatever you like. The chaining is that you link the cards together so that on the nth card, if you will, you have the index of the previous card, the n-first card. Right? And that's a very important, that's not a new innovation that's been around for a while, but it gives your cards naturally a temporal ordering, which you want, for example, if they're tracking transactions. So there'll be a first card, and then on the second card, you'll have the index of the first card, on the third, and so forth. So what that means is I can give you the index of the latest card, and you can go to the pool of all the index cards, and you can pull them out in order, and you can sort of see the connections between them.
The chain.
The chain, right. So that's why it's that's the chain part of the blockchain.
It's very descriptive, blockchain.
It is good.
Yeah.
The second thing it has is when you use a database, as a user, if you take a copy of it, you are concerned that you have a copy with integrity, that it is an accurate copy of the original database. And the blockchain uses a very clever way of determining integrity using what are called hash functions.
Right.
So hash functions they really are a magical ingredient in this whole thing. What a hash function does is it takes an arbitrarily lengthed input and it produces a fixed length output. Okay, so the classic example we all love from IT systems is we're going to make your email address, and it's going to be the last 5 letters of or the first 5 letters of your last name and your first initial.
Yeah.
Okay? And that's kind of useless because if your name is Jim Smith, there'll be a lot of J Smiths in there, and you get what are called hash collisions, where two distinct things hash to the same
Address,
two inputs to it.
Yeah.
So there are more sophisticated hash functions, though, where the chances that different inputs hash to the same output is extraordinarily low. And I'm not talking low in the 1 in 100, PML sense here. We're talking about low as in the chances of picking a particular atom from the universe, right? To all practical purposes, it is not going to happen. So how is this used? Well, what you do is you take your index card, you take the contents, you run it through your hash function, and then you use the hash as the index. Okay, so now if I download an index card from the database, I can check that I've got a good copy of it because I hash the contents. If the answer I get doesn't match the hash of the index on the card, something must have happened in download, and I don't have a copy with integrity.
Mm-hmm. Okay. Why do we do that? Why do we need a copy with integrity?
Well, because it's money or something. We're storing bank balances. We need to know that we've got the actual. It actually matters.
Yeah, there's and I was just mentioning before we started. There's a metaphor that I was thinking of yesterday, which is if Bitcoin, call it this asset of value, the equivalent kind of real physical idea is if we all took our money, pulled it out of the bank, dropped it in the middle of the town square in a big pile, and then turned around and walked away. And we're sure, actually, that it was all going to be there in the right order for everybody, every single person, when we got back, and we can use it whenever we wanted. But it was just sitting there in front of everybody. Anybody could walk up to it and touch it and look at it and see who's in principle. And so, like, the technology that enables that is fundamentally, I think, just, confusing is not the right word, but kind of mind-bending.
It is mind-bending. And here's, as I was looking into this was one of the things that bent my mind is, so the next thing that you do, that you realize is if you've created your index as the hash of the contents. Part of that is the hash of the previous card.
Yeah.
So what that means is I can give you one 77-digit number, and you can download the entire Bitcoin database, which I checked this morning. It's 250 gigabytes right now. So 250 gigabyte file, you can download it. You can do what is in essence a really big ass computation. And if at the end of that computation you get the same 77-digit number that I told you is the current key, you can be essentially absolutely certain that you have a faithful copy of the original database.
Because
I find that amazing. So one number, 250 gigabytes of data.
Yeah, I'm going to come back to that actually in a second, but I just want to let's really put a finger on how important that is, because what somebody could do is they could give you the wrong copy of the database, where at the end of that chain is all Bitcoin goes to me.
Yeah, right.
And they say, they distribute to everybody, so here everybody, here's a new block, it's going into all your blockchains, and the end of that blockchain is all the Bitcoins go to me, I am now a trillionaire. Right, and so there are reasons, and we'll get into some reasons why that's not possible. But that's what's at stake potentially, is that you could get all that money.
Exactly. So, and that actually brings us to the next point. So we are sure that data has integrity, but in databases there's a difference between data having integrity and data having validity.
Okay.
We want the data to be a valid record of what we think is the true state of the world. Right. That we call validity, as opposed to. You can have a copy with integrity of incorrect or invalid data, right? So there's sort of two distinct issues. So the second thing that happens with blockchain...
Sorry, let me just come back to that idea. So that would be, it is a blockchain which is valid in the sense that it's a true blockchain, but it's got the wrong people who have the money? Is that what you mean?
It's if I make up a new block at the end, which is not valid, you can have a copy of it that's accurate, it's got integrity, but it's not valid.
Yeah, okay.
Right. So I've done your example, I've said all the Bitcoin goes to me. That's not valid.
Yeah.
You've got a perfect copy of an invalid record.
Right, yes.
Okay?
Yes,
right.
yes.
So
okay.
validity is the more important in many ways.
Yeah, sure. Great people have the money.
And
I still have my money.
This was the brilliant idea. You talked about proof of work. And the issue that we have here is computing all these hashes and what have you, very quick and very easy. So if we imagine we've got our key value database and you want to go back and you want to change a card in history so that it transfers all the money to you, well, there's nothing to stop you doing that calculation. You can then recompute from that point forward, do all the subsequent keys, and you can then present this to the world as this is the state of the world. Yep. Okay, and people could download two copies with integrity, but they wouldn't know which is which. So we need a way to build sequentially and at each step have everyone agree, and then have a way for that not to be able to be changed.
And so
okay?
let me pause there for a second and talk about BitGold again, which is probably a better way of inserting that. Where under BitGold, what the inventor of that, named Nick Szabo, his idea was we're going to have everybody vote. And so everybody who's in this network now is going to have a vote. And he had a very complicated voting mechanism for which one is true. And it had to have some kind of consensus that was developed. And it was a really complicated idea and complicated piece of software. But Bitcoin's solution, Satoshi Nakamoto, who we'll probably get in touch, we'll talk about that in a second, about who that maybe person was, had a different idea for how do you all agree?
Yeah. So his idea is as follows. Let's suppose we're in a situation where everybody agrees on, we've got a stack of cards that everyone agrees on, and they basically tell us who owns what from this pile of money that the village has put into the town square.
Yeah.
And now we've got a number of new transactions, and we want to sort of lock some of those down. Okay? So people can look, they've got the existing record, which we all agree on. They can look at the new transactions, and they can check, this is, person A transfers to person B $10. Well, did person A have $10? Yes. Okay, that's a valid transaction, right? So we can assemble a number of valid transactions together. We're going to write those on our index card, and then here's the secret sauce. Normally, we would just then take the hash of that, use that as the index, and that ensures that we can guarantee integrity. The extra step is as follows. We want to actually add a little extra piece to the card so that when we hash it, we get a small number. The hash that comes out is a small number because these they're just numbers, right? It's literally a 77-digit decimal number. And they're essentially randomly distributed, right? So if I start with a payroll load, it's got a bunch of PDFs of transactions in, and I just add an integer at the end and I increment it. I do that often enough. Eventually, I will get a hash that comes out that's small. It begins with a bunch of zeros, okay? And by adjusting how small it has to be, you can make that problem more or less difficult, okay? So what we do with the peer-to-peer validation is the group agrees, okay, at the moment we can perform so many hashes a second, so we want the number to be below whatever the threshold is, and people scurry away. They try and find it's called a nonce, a number used once that you add to the card. They try and find the nonce so that the hash is small. As soon as they find one, they broadcast it to the network and they say, okay, here's a card, list of transactions with a nonce that locks it in. Everybody looks at it and they can then all validate, yep, all those transactions are valid. We all agree with that. All right, that's now a valid card. I put it on the pile. And now we all start working on the next card.
Yeah.
Okay. And the reason that this works is now if I want to change, let's say I want to go back 2 cards and I want to change a transaction on that card, I need to find the hash for that card. Then that changes the next card, because remember the index comes through onto the next card. So I need to find the nonce for the next card and so forth. But meanwhile, everyone else is working from the sort of front of the caterpillar, if you will, and they've moved ahead, and you'll never catch up. Okay, so in that way, it becomes essentially impossible for someone to go back and change history because you've made it difficult to kind of mint the new cards.
Let's keep dwelling on this topic. This is really important, and there's a lot of interesting complexities to it. So the solution that we're talking about here is to what, if I remember this right, maybe you know more about this than me, but the Byzantine Generals problem, which is if you're all sitting on a battlefield, right, and you're surrounding the enemy, your allies, some of them are pretty far away. So how do you coordinate? So if you're the general and you have a bunch of allies that are somewhere else on the battlefield, how do you get the message to them to attack now, or attack later, or wait, right? So they can act in an uncoordinated fashion and all go the wrong direction and lose the battle. And so what's amazing about this network is that, so back to the village square idea, we have a stack of index cards which tells everybody who owns what in the big pile of money. But everybody is now trying to validate the next card that's going to own. So we all have a card we're writing something down on, and the first person to get to the stack and put it on top gets the right stack. But what if we disagree? So now what if there are 2 messages that are getting circulated through the Byzantine Generals' army? Which one's right? And so I think that the way that Bitcoin solves this problem is that everybody shares with everybody else. So you have this network, this sort of multi-connected network where, I'm looking at the last stack from computer A over here, and there's computer D, which has another last stack, and they're all kind of agreeing. But if 2 consensuses emerge, so there's one group which is saying this is true, this is the new card to go on the stack, and another group is disagreeing with them, and you have a split. And it's happened a couple of times in Bitcoin's history. How do you resolve that? Well, you resolve that by eventually one of them is going to overwhelm the other one because they're going to keep adding more stacks on top of theirs. And then one of the, like you were saying, it's very hard to add cards to a stack because deliberately solving this little cryptographic puzzle costs resources. And so people may have heard of the 50% plus 1 attack. And that is you need to control 51% of the resources of the whole network because you have to be able to keep resolving what the next card on the stack needs to be. And you can have 2 stacks that are racing each other is the point. So when the cards disagree, when you have 2 different ideas for who owns what stuff, they start a race. And eventually one of them is going to win because their stack's going to grow faster and then they're going to spread more through the network. And the secondary stack becomes totally invalid. So all their cards, to the extent they disagree, become discarded and they just go away and they disappear. And then the stack that gets largest wins, and then that becomes the truth of who owns what.
The longest chain defines the truth.
Longest chain defines the truth, exactly. And there's this sort of, and as one of the things I was reading about in this research for this was there are 2 pages of the 8 of the Nakamoto paper, the Bitcoin white paper, which define the protocol, which deal with this. And that was the innovation that was of the evolution from BitGold to Bitcoin. Because if you have this voting mechanism, which says answer the question of who owns what. Let's all vote on who owns what. Let's look at a town square and let's raise our hand and I vote this way. Complicated to implement. Bitcoin says we're not gonna think about who's right. We're just gonna make sure that we're going to ensure that the one who is right is the one who has the biggest stack. The one who has the biggest stack is the one who controls the most computing power to solve these cryptographic puzzles. And that's the only value. That's the only arbiter of truth.
It's an unforgeable. You can't. You could pretend to vote, or you could vote not your true intention. You can't make up computing power. You actually have to have it. There's no substitute for it.
Yeah.
So another thing which we didn't cover, but that's very important on this validation is, so why do they want to be the next person to add the top card to the stack?
Sure.
And the reason for that in Bitcoin is, well, you get paid for it.
Yep.
Okay. And that's an important part of the incentives that when we think about applications of blockchain in other areas, you need to think about, well, if you're going to want some equivalent to miners, how are they going to get paid? And people often miss
And
miss
paid
that.
in two ways. And I learned this recently, only recently. One, you get rewarded coins as once you successfully mine a new card. So once you successfully put another card on top of the stack, you're handed some coins, right? And the second actual way is you do get paid transaction fees on the Bitcoin network. So it costs Bitcoin to send Bitcoin to somebody else. Right now, the transaction fees for Bitcoin is $50 to actually send a transaction, if I think I have that right. And so there is a fee element baked in there, which the miners also get over time. And that can grow or shrink or whatever. There's a market price for all that as well.
Yeah, so the way you may have also heard there's going to be 21 million Bitcoins.
Yes.
So how does that happen?
Yes.
Well, the whole network is calibrated to produce one block every 10 minutes. And it started off that you got 50 Bitcoins for minting a block. And then every 2 years that halves. It's currently down to 12.5 Bitcoins per block. And it'll keep halving. And obviously, you sum the geometric series, it's going to max out at about 21 million Bitcoins will be issued.
Mm-hmm. And so let's just maybe recap now on the technologies that we've talked about, because I don't know how good of a job we're doing at explaining this, because it's one of the things that really gets to me about learning about this is that they're unfamiliar topics. Not used to thinking about stuff like this. This is not, oh, my computer's faster than it was, and therefore I understand the implications of that. These are genuinely surprising ideas. And so we have the public key cryptography, which is one idea here, right? Which is how can we secure that the transactions that I sent money to you and you know it came from me and that's a valid transaction. And we have these puzzles, the nonces you're talking about, which make adding a card to the stack hard, arbitrarily so. And those are adjusted over time to make sure that we only get 10 transactions, what is it?
10 minutes per transaction.
10 minutes
six now.
per transaction. Any other key technologies here that we're missing? Like genuine technologies that computers do. What else do computers do?
So the nonces is relying on the hash functions, which are magical. There's a digital signature concept, which means that you can sign a document in such a way that you can tell it hasn't been tampered.
Yep.
But that essentially uses the same ideas as public key encryption.
Yeah.
And then the fact it relies on the network and peer-to-peer communication.
And the rest of it's social organization.
It is. It's an extremely clever and ingenious combination of existing technologies.
Yeah.
There's no new technology or concept produced for this, but the parts were pulled together in an incredibly imaginative and creative way.
Yeah, and I think that the idea of, as I said before, throwing your money in the village square and then knowing that it's safe is so surprising that I think that one of the reasons why folks, including me, have a hard time understanding the implications here is like, what else is possible in a world where that can be true?
Yeah, so we've sort of discussed on the blockchain. We've discussed it's a database, it's a chain key value database. We've got the hash enforced integrity. We've got the peer-to-peer validation. The missing piece that we haven't discussed yet is so just what is it that the Bitcoin network stores in this database?
Right.
That's
idea.
kind of all like a container, it's like a SQL database. Well,
Yes.
What are we putting in it? Right?
Yes.
And what we're putting in it is ownership of the Bitcoins. And the way that ownership is sort of asserted and transferred is if you own some Bitcoin and you're going to send them to me, the way that works is I give you a puzzle to which I know the answer, but it's very hard to determine the answer. Mm-hmm. And what you do is you've similarly, when you got the Bitcoin, you had some puzzle to which you know the answer, and you essentially sign it over. You can almost imagine it as being like dollar bills, and there's the puzzle on there, and your puzzle was given, when it was given to you, it had your puzzle on. You write the answer on, and that's what everyone, when they validate the blocks, they validate that your answer is the answer to the puzzle on the card, on the dollar bill at the moment. Mm-hmm. And then I give you my puzzle, you write my puzzle on there, and then the trick though is, it's not like a dollar bill in that you give it to me, you just broadcast it to the network. So it's called a UTXO, an unspent transaction output. There is on the network, there is this puzzle sitting there, and it has the rights to claim so many Bitcoin outputs, and it's accessible by anyone who can answer the puzzle. Right? Now, I know the answer, but in theory, somebody else could figure the answer out, and they could whip it away, right? I mean,
this being your key. This is the idea of private and public key.
This is your private key, and it's quite part of the the design is it's sort of protected by about 3 layers of concepts, so that if someone figured out how to reverse engineer a hash, well, it's actually double hash with 2 different algorithms, so you'd have to solve 2 different algorithms, not one, and then you'd have to solve something called the discrete logarithm problem, which is widely regarded to be an impossible problem to solve with current technology.
Let's talk about hashes for a second. So the magic of a hash function. So, and the way it would describe to me as I was researching this is, you could take a whole novel and you could hash that into this, 72 integer number?
77, yeah.
77 integer number, right? Or you could hash the word dog into a 77 integer number.
So, yeah, and so when I started playing around with this, I was like, oh, well, I don't believe that. That seems like nonsense, right? Yeah, unbelievable. So I took a photograph, and I hashed a photograph, and I got a number, and I'm like, right. And I went into Photoshop, and I changed 1 pixel and hashed it again. And it isn't like the last digit of the hash. It's a completely different number, right? It's a totally different number.
Yeah.
And the way sort of underneath they work is they take your input file, it's divided into chunks, and then on the basis of each chunk, it sort of does some shuffling. It's like you're doing some riffle shuffling, and maybe you divide the stack of cards into little bits, and then you shuffle the blocks around. And it's just a sufficiently complicated thing that, as far as we know, you can't reverse engineer it. It's called the one that there's a number of them. Bitcoin uses one called SHA-256, which is secure hashing algorithm. The 256 is it works with 256-digit binary numbers, which then translates into a 77-digit decimal number.
And so there are 2 different keys that were used. There's a public key and a private key, and I think of them as a lock and a key, right? So your public key in some ways operates like a lock, where it says in order to get into that lock and open it up and use the Bitcoin or take it, you need to have your private key, which is kind of more like a key. And I think that if I can get this metaphor right, what we're saying here is that every key is defined by some kind of, well, it's a password, I guess, right? And changing a little bit will completely change the configuration of the lock, and so the key looks nothing like the key you had before, even though you changed it only a little bit. Yes. And you have to have that key. Somebody can steal your key.
Yes, so this is a much underappreciated fact, is that you can't solve the problem, but people can't remember 77-digit numbers, so they need to write them down somewhere. And they can be stolen, and they can also be lost, right?
Yeah.
I put them on a flash drive, and that got thrown away. It was in the Silicon Valley. The guy left it in his jeans pants pocket.
Yeah.
So that's again, and I'll probably get to this, but the sort of interface between the real world and the digital world. In a closed digital environment, yes, it's all perfectly secure and what have you, but the keys do live somewhere, and if you get that key, you can transfer that money, and you cannot get it back. Right? It's a gone.
Mm-hmm. And let's come back to what actually is stored on the blockchain. And my kind of understanding of it is that it's a list of transactions. So what's interesting about the Bitcoin blockchain, as distinct from, say, Ethereum, which I'm sure we'll touch on here, is that Bitcoin doesn't actually say this person has this much money, this person has that much money. It says, throughout history, here's all the transfers. Starting with the first transfer, here's a giant list of all the transactions that have occurred, which is not the same thing as saying here's a list of the accounts and who has what. It's saying here's where the money flowed. It's not stocks.
Correct. There's no notion of an account. An individual can have multiple addresses. It is simply a tally of the problems to which your private key is the solution.
Yep.
And then and people match them up, and that's it.
And one of the things that we've been playing around with some blockchain software, and in preparation for this mostly, and you can get call it a plugin for your browser or whatever it is, a wallet application, and that you say I own this much Bitcoin, and you can put in an address. You just copy and paste this giant number, and you say send it to this address, and that might be the first time that the blockchain for Bitcoin saw that address. That's okay, right? That address doesn't exist somewhere else. It's you just made up this number, and then now on the blockchain it just says this number has this many Bitcoin, was transferred this many Bitcoin, and if you have access to the key which can decode that number, you can then send it to somebody else.
Yes,
if you want.
In the same way, they will give you their problem, and you just sign it over. You very much can think of it as it's like a check that you keep endorsing.
Yeah, and one of the key ideas here is that you can have security without ownership. And the ownership here is where you think of like distinct from a bank. And that was just coming to my mind just a second ago now, where if I want to send the money to somebody else, I'm back at TD, right? And if I want to send money to somebody else, they have to open a TD bank account in order for me to send them a TD send the money on the TD network, and other bank accounts, of course, do. But you have to open an account first. But with blockchain, you don't. You just send it to an address, and as long as somebody can grab that address, you don't have to open an account or close an account or monitor an account because nobody actually owns the account.
Yeah, it's a somewhat surreal experience. I taught in my class last year. I taught about how Bitcoin worked as sort of part of a fintech module, and I thought, well, I should know about this in reality rather than just in theory. So I should go and buy some Bitcoin. So down on Prince Street here in New York, there's a Bitcoin cash station. And you trundle up to it with I put $200 into it, and you have your address, and it's one of those quick response codes. You hold your phone up to the camera, it scans the code, scans the number in, you put your $200 in, and that's it. It's actually not quite it. There's a little more regulation in New York. You actually have to provide a cell phone number so they can tie ownership, which is, that's a whole sort of the security apparatus of money.
Off-chain.
Different thing. But I sort of walked away from this, and I'm thinking, well, so where did my $200 just go?
Yeah.
What happened to it?
It is now gone.
And one of the confusing things is a lot of the Bitcoin software will provide you with what are called wallets. And wallets are ways of managing your private keys, managing if you want to send money. They figure out what outputs you've got, and they build the transactions for you and what have you. But your money does not live in your wallet. Your money is, your ownership of your money is from your having this number which corresponds to a problem on this distributed ledger.
Yeah.
And you can kind of see that the money doesn't live in your wallet because you could put the same money, the same Bitcoin, into hundreds of different wallets.
Yeah.
But you can only spend it once. If you try and spend the same Bitcoin twice, what'll happen? This is where we go to the validating transactions. So I could take my same private key, I could put it into two different wallets, and then I could simultaneously try and spend it to two different places. Well, what's going to happen is people assemble the next card, they will pull one of those transactions, maybe as the first one, but when they get to the second one, they'll go, no, this one's not valid, I'm not putting it in, because they can see that right there. And so, on that incremental building the new card, you solve the double spend problem.
Yeah. So the key doesn't actually give you necessarily ownership in some conventional way. It gives you the ability to send it somewhere else.
Yes.
Which is kind of ownership, but in other ways, because it gives you control,
It gives you control
over that.
Yeah.
But it's not. I feel like it's only it's subtly different from what we think of typically as ownership, maybe, but in name, but maybe not necessarily in effect.
Well, and it's interesting to ponder that from a state and legal perspective, could you prove that someone owned some Bitcoins, right?
Right.
So essentially the only way that you could do that would be to find the key. Now, the person, if they had a good enough memory and they were confident in it, they could literally just remember the number.
Yeah.
And there was nothing physical written down. So at that point, it would be impossible to prove that you actually own. So you've got effective ownership. You can control it. You can spend it, but an outside third party could not prove it. And for example, there's an address out there. I think it still exists that had 450,000 Bitcoins in. At $6,000 plus or minus each, that's $2.7 billion.
Right.
Which some guy could be walking around with literally the key to that in his head.
Yeah.
Or it sort of blows your mind.
It was in his head, and he got hit by a truck.
Right. And then that's a...
What happens to that now?
It's gone, and it's gone forever.
Or it sits there on the blockchain.
It sits there on the blockchain, but it never moves. It never gets spent.
It will never, yeah.
There was actually an article in the journal I saw the other day about a company helping people try and recover lost Bitcoin.
Yeah.
But they're not doing it by solving the problem. They're doing it by someone's got a wallet that's encrypted, and they try and decrypt the wallet to get into the underlying coins, which is an easier, it's basically just password cracking. So that's an easier
I see, yes, because you have to come up with a passphrase or a password in order to get into the wallet itself. The wallet holds the key.
The wallet holds the key.
Yes.
So it's just like a password encrypted.
It's a less
zip file
secure version of the same thing.
Yes. Very much less secure.
Yeah. Isn't that amazing? Yeah. So maybe we can talk a little bit about other Bitcoin technologies, in particular Ethereum. So Ethereum is another blockchain which was created, and Ethereum is very different. So Ethereum is the metaphor that the founder of Ethereum, this guy is like 22 years old, named Vitalik Buterin, really interesting guy, came up with it when he was a teenager. Canadian, Russian Canadian, but grew up in Toronto, and his Ethereum is. He looked at Bitcoin and he saw that actually within Bitcoin there's a tiny little scripting language, and maybe we can talk a little bit about that first. And so that the scripting language says, do this, so you can send it money here, and when you're actually sending coins. Or when you're executing a transaction in Bitcoin, you have to specify a few specific parameters. You want to talk a bit about that, Steve?
Yeah, sure. So the scripting language for Bitcoin is how you express the puzzle.
Yeah.
So the most common script in Bitcoin is pay to public key hash. So the idea there is I'm going to send down the wire a few numbers, and this scripting language is going to execute a few transactions with them. And what it's essentially going to do is it's going to take my public key, it's going to hash it, and it's going to check that the answer is the answer that was given when the Bitcoin was transferred to me. And then it's also going to validate. I'm going to sign the transaction. So I'm signing that I'm the only person who could sign this transaction.
I have the key.
It proves that I have the private key that goes with this public key. So it was kept deliberately simple. I mean, in particular, there's no looping and no branching in the Bitcoin. It's essentially a stack. You push things onto the stack. There's operators, and then eventually they collapse down. And when it ends, if there's anything not that it doesn't evaluate to true, the transaction is not valid. With Ethereum, they built a much more sophisticated scripting language. It's a Turing complete language. You've got loops and what have you, so you can really express anything in it, and it allows you to have much more complicated ways to unlock ownership. But just going back to on Bitcoin, you can already do some fairly sophisticated things there, right? So you can set up a Bitcoin address, and you can say this Bitcoin address will pay if 3 out of 5 of these addresses agree, for example, which is, that's quite sophisticated. There's an N of M. I forget what the exact limits are. But it's sort of within bounds, but you can get quite creative with that. Ethereum, on the other hand, full programming language. So to the extent you can sort of get inputs in that everyone trusts, you can do much, much more sophisticated things with that. The downside of that, of course, is all of this stuff is non-reversible. So you've got to debug your little program very, very carefully. And there was a very well-known example when Ethereum first started of someone ran a script in some untoward way, and it blew up, hundreds of millions of dollars worth of Ethereum. And I think they actually went back and forked the network to undo that transaction.
Mm-hmm. Maybe we can actually pause for a little bit longer on Bitcoin before we go to Ethereum, and we'll get to it, I'm sure, and talk about oracles, because the idea here is that you can trigger a transfer of Bitcoin if, as you say, this other wallet here agrees. And so that other wallet can just be, or that address can be some other program that will flip to true, but through any condition. So it can be a computer somewhere. You can say when it's midnight, or when Johnny just hits yes on his machine, or anything else. Or let's talk a bit about oracles and how they might be able to affect Bitcoin, and then we'll talk about them also for for Ethereum too.
Yeah, so we're getting here into this the real world, digital world kind of interface, which when you're within the Bitcoin or Ethereum worlds, you don't have to worry about that, right? There is no real world. And to the extent Bitcoin or Ethereum encapsulates value, you've sort of got everything you need for a lot of financial transactions right there. You don't have to worry about connecting out. As soon as you connect out, though, yes, you need some type of an oracle to be an arbiter of the truth. This is why it's called oracle. So Authorityless, for example, the travel insurance, I think they sort of tack into TSA and the sort of, not the TSA, the FAA, that does all the flight delays. So you can get pretty much globally a definitive listing of, was this flight on time? When did it take off? When did it land? When was it scheduled? And
you trust them.
They use that as the oracle to pay out travel insurance, right? I buy if my flight's delayed more than 2 hours, $100, and it's then all handled through this oracle. So that's a nice example. The building good oracles, though, very difficult, right? And as soon as you get to something that's not definitive and black and white, is going to be a problem, and that's going to be a path that needs a lot of work.
Well, what's interesting to me about this is that all this public key, private key, all this stuff, all that ensures is that everything inside of the Bitcoin system is true. and trustworthy, right? It is the truth. But once you start including oracles, now you're introducing outside elements which may or may not be trustworthy. And so it's nice that you have this little walled garden here that you can trust. So the money in the pile in the village square, we're okay with that. But as soon as you start relying on external parties or external systems to start helping adjudicate what money goes where, now we've introduced security concerns. Maybe someone now can hijack the oracle and steal the money.
Yeah, and you get to, I mean, sort of a classic example that people are thinking of using this for in insurance is contract certainty. And so you get to, well, who needs to agree? Who needs to be the oracle, right? You can get to contract certainty using some of the capabilities that we've discussed, digital signatures in particular, right? That the parties could circulate a PDF, they all agree, they can digitally sign it. You can then tell whether the document has been forged or changed in some way. And you can do that using just a piece of the capabilities here. But you do need to rely on, somebody needs to become the keeper of the contract and the keeper of the signatures. And
Somebody needs to own it.
Yes.
And I want to pause here and dwell on this for another second, because the part here that I wrestle with is I'm not used to thinking about security. I'm not used to thinking about what is safe. We live in a pretty safe society for the most part. And in particular, the only things that really hit the mainstream on the internet are things that are pretty secure. And so the reason they're secure is that there's a trusted authority which owns it or manages it or ensures its security. And we just, even if only implicitly, we more or less trust all these authorities. And that's a part of our society which some people lament. In particular, the kind of folks that start cryptocurrencies lament that kind of thing, because you have all kinds of knock-on problems, such as like too big to fail banks, where nobody actually really scrutinizes whether these organizations or institutions deserve our faith. We kind of just assume everything does, and if they don't, the government will come in and whop it up in the ultimate backstop of security. And we live in a society, I think, that because we don't think too much about security and safety, I think a lot of the ideas that blockchain pulls out or uses or changes are just unfamiliar to us. We're not used to thinking, well, what if we didn't need an institution to ensure the security of our money? What does that mean about other things? And it's taking me a long time, and I'm still kind of working through it, of what the implications of that are. And I don't know where I'm going to wind up there. And I think that it's easy for people's eyes to glaze over when we talk about, oh, it's secure. And I remember mine doing this too. The first few times I heard about all this, I don't even know, like, why do I care? Why do I care that the public key cryptography works? Like,
I think on that is an interesting point about one of the reasons we trust security is if something's wrong, you can generally get it fixed.
Yeah.
Right? So you have some credit fraud and someone opens a credit card in your name, you just sign your affidavit, this wasn't me, I never shop at this place, I was in a different city at the time, and it all gets reversed out and you're good to go. Blockchain sort of, Bitcoin in particular, it doesn't work like that, right? Someone spends your Bitcoin, it's gone. You never, there's no 1-800 number. Oh, I lost my keys. 1-800 number. Please reset my password.
Yeah.
Not happening.
Poof.
So it's a very different security model.
And there's the most important uses for Bitcoin, as I've observed them in the world, do emerge where you have those trusted institutions are failing. So think of, for example, the main use of Bitcoin, some will say, and I think I probably am sympathetic to this idea, is it exists to evade currency controls. So you have Venezuela, you have hyperinflation, you have China where you have currency controls, money can't leave the country, and when China cracked down on Bitcoin, the price collapsed. And so the uses of these, and for that matter, you have drug trade. Right?
Didn't someone describe Bitcoin as solving math problems and getting drugs?
Yeah, right. So these are instances where you either don't trust the authorities or the authorities don't trust you. In either case, if you're a drug dealer, you don't trust the authorities because they're out to get you. And so Bitcoin exists where there's a breakdown in trust, and it supplements that trust with a secure network that you can then trust yourself. And so in a society like we live in, where trust is pretty functional in most institutions in the United States, where Steve and I both sit, although we're both from other high trust countries, the UK and Canada, what's the point? Like, is it really going to do anything for us? So maybe we can pause on that question, and switch to Ethereum for a second. We'll come back to sort of the bigger business implications of Bitcoin and blockchain. But Ethereum. So Ethereum is not a list of transactions. Ethereum's a list of accounts. It's a list of what they call it, the state. So it's a list of state instances where this account has this account has that, this account has that, which is a different conception of the blockchain. Steve, any thoughts there, comments?
Correct. Yeah. And it was actually forked off Bitcoin originally, right? So if you go far enough back, was the same thing. And I guess one thing to mention, keying off that, is that the Bitcoin database that's the ledger of who owns what is a completely useless database other than for determining who owns what. It is, it doesn't maintain state. So if you actually want to see, accumulate transactions by address or something, you need to take all the information out of that database and put it into a much more sensible database format. So it really is just a solution.
It's very narrow.
Determining the truth. Okay.
Yeah.
And I think it's a good question you bring up is, in a world where by and large we don't have a problem determining the truth, where is that application? But I think where it is in part, you talk to banks, you talk to insurance companies, people spend an inordinate amount of time coming to agreement on the truth. Mm-hmm. I've got my books and my accounts, and I think it's this, and you think it's that, and then we'll back and forth. And so there actually is, it's not exactly a trust issue, it's an efficiency in getting to the truth issue. And I think that's where, Jamie Dimon is obviously very down on Bitcoin, but pretty bullish on blockchain, because I think he sees the technology as helping with efficiency of transactions behind the scenes.
Mm-hmm. Because he can trust that something has happened, that is, a transfer has happened of some sort, and so it reduces the cost.
Yeah, and I've got my own copy of it, but you've got your own copy of it, and we're all assured that we're all looking at the same thing. Yeah. We're all on the same page, right?
Yeah. Because it's so expensive to hijack that network and make your own stack of cards that it's hard to do that. So maybe we can talk a bit about what this means for the business world. My own, I spent some time in researching this, building a D app on Ethereum. In Ethereum, having this Turing-complete programming language, you can more or less program anything you want. And what I discovered was that, so my idea that we were talking about was, what would an insurance company that looked like that was sitting on the blockchain? And what I found myself doing was more or less re-implementing a policy management system, but on the blockchain. And it kind of sat back and it occurred to me, this isn't, one way of looking at Ethereum is, it's a very slow, very, very junky computer. It's as the founder made the point in an interview, he said, Ethereum, running a program in Ethereum, though it's this Turing complete programming language, it's kind of like running it on a smartphone from 1999. It's got terrible memory capacity, it's really, really slow, and the reason for that is that the transaction needs to be run simultaneously by thousands, millions of different computers. And so it's really expensive way to actually achieve something in some very weird ways. It's actually very primitive technology. But yet it has this component of trust, which is new, which is different, and we're trying to still figure out what it means. So back to the insurance company idea, what parts of an insurance company actually are worth doing more slowly, but worth doing in a more open, trustworthy fashion? Likewise with other technologies too.
Well, okay, so I think there's a few more related technologies to blockchain that I think open up a huge vista of opportunity for us, right? And I would call this, what we sit in a world where you've said we all trust one another and sort of the thing basically functions okay, but then on the other hand, we have Equifax.
Sure.
Sitting there with all of our credit information, which was all stolen,
Oops.
right? And costing, so it doesn't, I mean, it costs us, let's face
perfect,
it, right?
Yeah,
the cost is socialized, but it comes through in the fees and what have you.
Yeah.
There's the capability here for us to kind of reassert ownership over our own private information. And this actually goes back to our last chat about is data labor or capital.
Yeah.
That we can pull it back. And we could imagine a distributed ledger database that contained, for example, our credit information, which would all be encrypted, to which we would hold the encryption keys. Mm-hmm. And it could be managed in such a way that if you wanted to apply for a credit card, then you would give the credit card company, you could give them a one-time read-only access to essentially look at your record, right? And you can manage it so that they can not write anything down. They could sort of get a yes or no answer. They would like run a script against it, which would give them a yes or no answer as to whether you're approved or not, but without them actually seeing the underlying information. And they could only do it once. It could only be called within a given time window, right? Let's compare that to the current situation. Currently, what do? You write your social security number down on a piece of paper and you give it to them.
Yeah.
They have now got access to your credit record in perpetuity. And I know there's laws around, when they can do it and when they can't, but it's not quite as reassuring to me as the idea that, no, I'm going to give you a key which will let you look at it once in the next 30 minutes and make a decision on this particular thing that I know about. And it seems to me that we need to think bigger than, oh, we're going to get all our contracts in sync. We're going to have contract certainty. That's just fantastic, that is, right? I mean, the insurance industry has been working for 300 years without perfect contract security. I think we can continue to manage with that. It would be great if we could get there, but, this private ownership of private information, and if we do it like this, you physically couldn't have an Equifax situation, right? The database is already, quote unquote, being hacked. It's already out there. Anyone who wants it can download a copy of it. All the information is protected behind sort of rock solid cryptographic algorithms. And there is no central repository of all the keys. Each individual keeps their own keys. Now we're back to our Oracle problem of how do we get the information in there, and you can do sort of interesting peer-to-peer validation. So and so is a good person. They're part of this network. You could get traditional kind of credit transactions and what have you in there, but it's solving this trust vacuum. I think is just an enormous potential for the technology we're looking at. And you might say, well, Steve, why aren't you out there raising money to do it? There's a few technical details. The business model that sits behind this is not quite clear, because it's going to be a business model that would require every individual to pay a sort of small amount to maintain a system. And we've very much gotten ourselves used to, we get paid in service for our data, but we give up our data. So it's sort of a shift. People don't like even paying $1 or $2. You pause. I don't know. I pause before I spend $3 on an app. It's like, well, why am I even thinking about this? What am I losing? But people do, right? So getting the business model for this is maybe difficult. But I think that just transformative potential for how we manage private information.
And so many of the applications for blockchain are distributed databases, they call them. So this is really databases being lists of things, and that's what a blockchain kind of is. It's a list that nobody can change without your permission. And so where is that security a problem? And I come back to the idea that for the most part, we have institutions which have developed to kind of make that work all right. And back to this point that Chris Dixon made, and I think it was Chris Dixon, but or maybe actually you made it, where you said it's kind of like in the 80s and 90s.
Chris Dixon made it originally.
Did he? Okay, right. So maybe you both did. So, and that's a long time ago on the internet. And think of like smartphones and the rest of that being a technology which emerged much, much later. And I've found just in using the tools of Ethereum to build an application online that it's clunky. Like it's evolving quickly. It's hard to build anything that's reliable. Most of my programming is done on very mature tools. Think of like Excel or even Python, which is evolving pretty quickly for a programming language. But man, it's still very stable and it always works. But the tools that you use to build things in the blockchain they're constantly changing.
We're at the Wright brothers stage.
Yeah,
we can fly across a football pitch.
Yeah, right.
Yeah,
right. And that makes it hard to. It's hard to know. Well, it's hard to rely on.
It's hard, and it also makes it somewhat hard to envisage, right? Because
yes.
it could take off, and we could get to the Boeing 747 of blockchain, or it could also fizzle out. We don't know. But as I looked into this, when I realized, okay, no, there is some genuinely magical capabilities here. Magical in the sense that you would not expect these things to be possible.
Yeah.
They are possible. and as I talk to people and try and do some education around this, what I want to try and get across is what are those magical components, so that as somebody evaluates a potential solution, if it's not using some of the magic, it's probably not the right solution.
Yeah,
right?
that's right.
If someone's pitching you, use a blockchain database because it's a database, it's almost certainly not the right solution.
It's probably the worst possible database.
It's probably the worst part, right?
Yeah.
So it needs to incorporate, your application needs to fundamentally incorporate. And it goes back to the trust as the key thing. If you don't have a trust problem, probably you don't want a trust solution.
Yeah, I mean, back to the insurance company example, you have what are basically pretty high trust institutions, insurance companies. They're backed by the state, by regulators, and all sorts of. They have an whole ecosystem of trust, which, in some ways, when you look online of the list of all the industries going to be transformed by blockchain, insurance is usually up there. And I agree with the sentiment, because insurance and all financial institutions are high trust institutions in the sense that you do need to trust them in order for them to work, right? So trust is incredibly important in our industry, but we already knew that. and we collectively, I mean, it emerged, of course, that all the different components of our business which exist to ensure and bolster trust amongst all the actors, they already exist.
Right, to some degree, right? And that's why I go back to trust vacuum, I go back to sort of credit monitoring, credit reporting. That actually doesn't work terribly well at all.
Right.
As if you moved, I don't know, when you moved here, what your experience was transferring your credit from Canada to the US.
Started fresh,
right?
Yeah.
I know people who've moved to England. Same issue. Try and get a bank account in England, even if you've got a reasonable amount of money to deposit.
Yeah.
No, not happening.
Here's an $800 credit card.
Well,
thanks.
Prepaid.
Yeah, prepaid.
So we've got the capability here, potential for a global system to do this. And so scaling that, and another book I read recently, Factfulness, that Hans Rosling book, talked about. By and large, there's a lot of companies today are thinking about more and more polished products to sell to a very small proportion of rich people in the world, and they should be thinking about so if there's 7 billion people in the world, there's somewhere between 500 million and 1 billion rich people. They're extraordinarily well served. But then there's about 5 billion people in the next bucket that are up and coming really very quickly and have got a reasonable amount of money to spend on certain things. That, if you're talking, what's your strategy for growing your business into the future, especially an insurance company, you should be thinking of policies that work for the next 5 billion people, not the top, billion or two. And there, this whole sort of distributed, let's get away from a country by country approach to a truly global approach. There's potential applications, I think.
And one of the things that bothers me a little bit about doing a podcast episode like this is that, let's call it, there are two camps of people out there, and I want there to be a third. So the camp number one are people who are looking for an opportunity to dismiss this, right? We might not even make it to this point in the show. We're going to say, yeah, they didn't like it either. Bang. All right, it was useless. And I feel better about myself now because I was dismissing it, and I have an excuse now to dismiss it. There's another camp that are probably listening to the same show and saying, these guys love it. And I love it too. And I think it's the greatest thing ever. And I'm going to start implementing all my dumb ideas that shouldn't be on the blockchain and put them in the blockchain. What's missing, and this is the thing that I think will emerge over time, is a considered approach of saying, this is really cool technology, but I'm not totally sure where it fits in. And you got to keep your eyes and ears open there, because something is going to change here, and I don't know, I'm not sure what it is. I think there's the idea of security without ownership is so deep and revolutionary that some stuff will never be the same once the right representation of that idea bites into an industry. It's just really, really hard to tell what it's going to be.
Yeah, I completely agree.
Yeah. So maybe talk about some other technologies that we think are genuinely good ideas and are interesting ideas. One thing that I know you're on to is the Lightning Network. Maybe you can explain a bit what that is and what that achieves and what problem that solves.
So Bitcoin, one of the issues with the Bitcoin network is scalability. It's as we discussed, it's calibrated to one block every 10 minutes. A block is limited to a megabyte in size. A transaction is about 300 bytes. So it translates into sort of somewhere between 5 to 7 transactions a second on the network. And for comparison, Visa can handle about 50,000 transactions a second, sort of at a peak rate.
Yeah.
So we got, and it is,
what a piece of crap.
Right, exactly. So the Lightning Network is a quite ingenious solution of saying, well, does every transaction actually need to be on the network? And the answer is no. What we actually would like to be able to do is kind of like when you go to a bar and you open a tab. We want to just be able to open it. And how does that process work? Well, you give them your credit card, and they run it to sort of validate, yep, this person's sort of good for a while, and then they just keep adding stuff to the tab, and then at the end, you settle up. Okay, so the Lightning Network very much enables that running of a tab, with a couple of sort of very ingenious twists. So let's start off. Let's suppose that we are going to transact, and let's imagine that the transactions could go either way, right? So maybe we would start and we would set up, we want a tab with, let's say, capacity of $5,000 each. So we would set up a Bitcoin account and we would each put $5,000 into the account. And we would set it up so that there was a transaction that we both held, which would pull our $5,000 back, okay? Yep. So before I put any money into the account, we both basically sign the contract which says any money that's in that account, we can split 5,000, 5,000. Then we fund it, right? So that's riskless because I can get my $5,000 back at that point, right? Then we do some transactions, and let's say I now owe you an extra $1,000. Okay, so what we do is we alter the transaction that recoups the money. So we say I give you a new transaction, which is all right. We can now pull the money back, and I get 4,000, and you get 6,000. Okay. Now at that point, there's a slight issue because I'm still sitting on the first transaction, which says we get it back 5,000, 5,000. So there's a way, quite an ingenious way, to invalidate that transaction. Okay. Because it hasn't actually been posted, so we're not changing something that's been posted. It's a potential transaction.
And the blockchain.
And there's a way to invalidate it, right?
Yeah, okay.
So that now means that between us, we can do literally millions of transactions, as fast as our computers can talk, to continuously update that tab. Is it 5,000, 5,000, or how's it moving up or down? And at any point, we've both got security that we can get our original deposit of money back. Or our actual currently owed balances back, right? Reflecting all the transactions. So, just think about that for collateralized reinsurance, for example, right? You would start off, one side would post, these are the premiums I'm going to pay. The other side would post up to the collateralized limit. And then, maybe you have an oracle, which is PCS or someone that says these are how the losses are falling out. And at each point, we're holding a transaction that lets us pull back, guaranteed, the right amount of money, and we can see it sitting there on the blockchain. No bank, no letter of credit, no nothing. That I think is a it's very interesting. It's I think in sort of beta at the moment, or maybe it's running on a small scale. There's a number of issues of do you need people to have just bilateral sort of pots of collateral, or can you go through a network? Well, obviously the name gives it away. You can go through a network, and there's sort of quite an ingenious way of allowing two people to communicate through intermediaries, where the intermediaries don't know anything about the rest of the network. It's sort of an onion encryption, basically. You sort of you encrypt and encrypt and encrypt, and at each point, a person can only encrypt what they need for the next node, and then so they sort of strip the outer piece of the onion off, and they give the rest over to the next person. They keep stripping, and then eventually it gets back to the the correct destination. So that's a very ingenious solution to sort of the collateral problem, which is a big part of insurance, right? Being insured that you're going to pay in some way.
The money's there.
And it's also a very nice example of how with and this is sort of computing, right? Always is you build what seems like a completely useless basic tool, but then you can build tools with the tool, and then you can build you just keep going and you bootstrap your way up. Once you've got a C compiler, the world's your oyster because you make any other compiler.
Yeah,
right? So,
every time I hear about a technology, and this is my experience working with it directly myself too, is that the technology itself isn't complicated. What's complicated is actually coming up with the right way of designing the interactions.
Yes.
So these are like I like to say now, I guess these are social technologies, because this is defining relationships and trust, and actually coding in a transfer of a coin to somebody is pretty simple thing to code.
Yeah.
It's like send to this address. That's it. But then it's like, who gets the address? And under what conditions do they get the address? And so actually the logic of computing, I find, relative to other So usually when I'm programming something or designing some kind of technology, usually the idea I'm trying to achieve is pretty simple, but the way to achieve it is kind of complicated. Like I have to do a fair bit of coding to like come out an intuition for, I don't know, some actuarial model or whatever it is that I've done, or have something display the way I want it to on a web page, which is something that humans know what they want. Like I just want it to be in the middle of the bleeping page, right? And so that's actually way, way, way harder to code than you think it is, because you have all the different browsers and the underlying technologies are all really complicated and blah, blah, blah. But with blockchain stuff, it's actually super simple to build, but really hard to know what to build and how it should be built and that it should work. And is it the right way? Or is somebody going to steal this money? Or I think all the social consequences are heavier. What do you think?
So I'm not sure I would completely agree with that. I think there's a number of subtle points. And so I got excessively into this. You know, as an academic, I have the summer off, so I don't have the summer off. I have to do research. But I researched the Bitcoin network. And this was the first time I'd always heard that computers either stored numbers in big endian or little endian format, which is, you know, is it most significant digit first or last. I'd never in my entire life had to deal with this.
Yeah.
Well, you're implementing Bitcoin, you have to deal with it, right? Because it's the hash function works on a bit stream or byte stream, and so it matters what order it's in, because if you switch the order, you're going to get a different answer. And Unix machines and Windows machines tend to use the different ordering. So there's a number of, you know, fairly grungy details there that need to be taken care of. There is also on the cryptography side a number of points where you have to be extraordinarily careful about how you use things. And this actually, sort of amusing, it goes back to in the Second World War at Bletchley Park in the UK, where they cracked the Enigma machine. And there was another machine called the Lorenz machine that was actually used for even higher level communications with Hitler and so forth. They essentially managed to crack that because one day one person sent the same message twice without changing the settings. And that was enough for there was a guy there who literally with a piece of paper and a pencil figured out how it had to work. And so that type of thing where people think, oh, you know, you can't crack this cryptography. But what if you use the same key twice in such and such a way? Could people do something? You have to be very, very careful about that sort of thing. So your implementation needs to take care of that. So I sort of agree with you, but I would sort of there's a number of quite interesting complexities behind.
I like that point, and it actually reminded me of something a point I wanted to make sure I made in this conversation, which is the tools of the blockchain are pretty esoteric. Right, we're public cryptography, hash functions, security, all this stuff, but and so that's like the implementation of cryptocurrencies, and you know, does it work? Can you ensure trust? That kind of stuff, fundamental stuff. But it is so different once you kind of assume that works, or just are convinced that it works, and maybe you're wrong, but I haven't really evaluated whether it works or not. You've gone farther than me because you know more about it than I do, for sure. But once you start saying, okay, assuming that the trust is there, how can this work in the real world? Like, what are we going to do with these ideas? And the implementation of that, given that the trust exists, is very, very different. It's a very different way of thinking. You don't have to know anything about hash functions to know that they work. And then, so what are the applications now out in the real world for this technology? That stuff I think of as much more of social innovation, and the technology, the tools that you have access to, which underlying those tools is really complicated stuff, are really straightforward.
Yeah,
it's like
and it's sort of, I think, you know, let's think about what happened with the internet, right? That we're going back to this real world, digital world interface. What has that looked like, and what's the revolution been there? It's Amazon warehouses, which are incredibly automated, right? But also fairly manual, employ hundreds of thousands of people.
Yeah.
Massive physical infrastructure to go with the digital solution. So I think it's you know, I think 10 years from now maybe we do this podcast again and we'll look back and we'll almost certainly go, man, we totally missed what the brilliant idea was. But I would be surprised if there weren't some truly transformative things that we're probably not thinking about right now that don't come out of this new capability.
Yeah. We haven't even talked about currencies, but I think we're going to have to end it. We're out of time. My guest today is Steve Mildenhall. Maybe we'll do a round 3 and we'll touch on some more things, implications of Bitcoin in a little bit. Steve, thanks for joining me today.
Thank you.